Right, good afternoon ladies and gents. Welcome back to another Measurements 4 experiment. This one is an experiment using signal generator and a oscilloscope and two mystery cables. We are looking at unbalanced feed line characteristics, and the idea is to identify what kind of feed lines are within these two mystery boxes. We know there are two cables, they are 100 meters each. And the length of cable is very important because we're going to do a time measurement with this cable. The setup very simple. We've got a pulse generator here. The pulse generator is going to give us pulses. If you zoom in slightly, you should be able to see T1 and T2. T1 being the on time and T2 being the off time. To control this instrument is a whole bunch of buttons. It doesn't have a knob. T1 currently displayed, T2 like that. A burst means we can have a burst function and let it burst for X amount of pulses and it will stop. Or I can make it a single pulse and we're going to use it in continuous mode. Volts peak to peak, that's my output. So I want to put in a nice strong 5 volt signal. And if there's an offset, my offset currently is set to be half from 0 volts, so 2.5 volts being there. Doesn't really matter the offset, but what matters is our signal. If you read the experiment, they would like us to generate a pulse of which the on time is at least 20 times less than the off time. So T1 must be very fast, T2 should be not so fast. So T1, to adjust, I can adjust here and make the on time 0.2 microseconds. That's quite fast. If I make T2 2 microseconds, that means I've got the ratio of 100 times difference. In order for us to see a signal on the output, I need to press the green button. So immediately we start noticing a couple of things here. If I make a small adjustment, we'll talk about the adjustment in a moment. Sorry. We have the following. We've got the pulses from the pulse generator going to a T junction, going back to channel 1 on the oscilloscope. So with channel 1 and using my cursor, I can actually now say I am putting into the cable about 3.1 volts. And if I go to cursor B, with reference from there, there's about nothing. So yeah, putting in 3.12 volts into the cable and I'm measuring that. Cable has got impedance. Here inside this 1914 box of mine, I've got a variable resistor which ranges between 1 ohm and 120 ohms. As I adjust this resistor, I can then very easily affect the resulting pulse coming out of the same measuring point where the pulse goes in. So imagine, cable goes in, there's 100 meters of cable inside the box, it comes out by the second port into the resistor and through something called a standing wave ratio and the reflection of energy, I can reflect energy going back into the cable, runs 100 meters and it returns then at the same point where it went in. And that's quite important for us in order for us to be able to understand what is happening here. I'm bringing a multimeter into this setup for a very clear reason. Here I've got the connector. If I set the multimeter up into ohms, we know that it is a small resistance. Then I can actually measure. Sit down. And from one side to the other side. Currently I'm looking at about whatever the resistance of this variable resistor is. So if I turn the knob all the way to the other side, it's more than 200. So if I go there, So there it goes, 900 ohms. So in fact up to a kilo ohm resistor inside here. If I turn it all the way to the other side, we expect a very small reading. So somewhere there is the impedance of the cable. And the idea with the resistor is we want it to absorb all the energy that comes through the system. So, a couple of observations. The signal jumps a bit, always remember there is something called a trigger level, it helps a lot. So, the following happens. If the resistance is very small, in this case I make it as small as about nothing, 2 ohms. And I connect it back to the cable, I notice a negative pulse. If I turn the knob and I get a positive pulse, doesn't matter what the value is, just make the observation. Then I measure the resistance to be bigger than a certain value. In this case about 700, but that doesn't matter. And then, as we turn the knob, you will notice that second pulse is going past the point where it is actually not observable. It becomes negative, it means it is lower than the cable impedance. If it's positive, it is bigger than the cable impedance inside. And that is very crucial for us to take note of, because we can now adjust this variable resistor until we do not see where that pulse was on the screen. And the moment I take it out, remember there is about now the resistance of A, and now I measure there 78 ohms. Now remember, multimeters, you want to have it the closest scale that is useful, and then I get 77.5 ohm. Aha, I hear somebody screaming in the background, 75 ohms, sir. Yes, the cable inside this box seems to be 75 ohms. How do I know it? Because when I connect a 75 ohm resistor to the cable, all the energy is absorbed by the resistor. There is nothing reflected back, which means this resistance equals the impedance of the cable, and there is no standing wave ratio that can cause a problem. Let's just check the second cable for now. I do not adjust anything, please observe. We simply connect it to the box. Remember, BNCs, turn and click. Connect the resistor to this output of the second cable, and you notice what? The same situation, the cable impedance is also 75 ohms. Why? Because there is no pulse reflecting. So you say, sir, why you give us two cables of the same impedance? I say, you're not observing very carefully. Let's go back to cable 1. There is something changing between the two cables. Let's just disconnect the resistor for now. Cable going in, open output, which means infinity or a very large resistance on the cable output. If I now do the same and I connect my connection back to the input of the second cable, give it a moment, what do we see? We see a similar picture. But now I can change my cursor positions. If I adjust the white line to say, that's the beginning of that pulse over there, and I adjust, where is my second cursor now? There it comes. And I say, okay, the time it takes for my pulse to run through the cable and come out here on cable 2 is now from cable A or cursor A to cursor B, and we can zoom in a bit, make it a bit more scientific. We can move the position. So let's just get a single pulse on the screen, because the more resolution you have, the more accurate your reading it will become. So let's move the brown cursor position to more or less there, and then cursor A, let's also move it to the starting point of the input pulse. So delta x, 832 nanoseconds. Remember, I'm not doing anything else. I'm just shifting from one cable to another cable. Cable 1 and cable 2 is being my experiment cables. And you observe with cable 1, the second pulse has taken longer to return to where it was in the first measurement. So that's your first thing to see, is the two cables, they have different velocity factors. So if I now adjust cursor B, and you want to know how much did it change, up until this point, delta x 1.01 microsecond. So that's amazing, even to me. So one cable, both being the same physical length of 100 meters, the time it takes for the pulse to run through the cable is different. And that time we have something called velocity factor. Now in your textbooks they have the formulas and you've got some mathematics to follow up. But if you take down the two timings that we have given you guys, 1.01 and 824 nanoseconds, you should be able to work out what will be your velocity factor if you compare it back to the speed of light. Cables do slow down energy. Cables do also slow down your processes, and we call it velocity factor. Putting the resistor back, let's just confirm for you guys. Positive pulse, resistor is now bigger than the impedance of the cable. A negative pulse, resistor here is smaller than the impedance of the cable. The change in time is because of the velocity factor between the two cables. Now in your task, we ask you to simply work out what is the velocity factors and the impedance. Now you know that, and once you've sorted that out, we would like you to tell me what is the physical brand or making of this cable that is in each box. What type of RG cable did I put and hide away from you? Thank you very much.